Previously on UV Viz, we talked about this definition of a chromophore and how chromophores allow molecules to absorb ultraviolet radiation, or aka UV light. So we said that if the molecules have one of these chromophores on them, that this maybe, just maybe, will allow it to be suitable to be analyzed in a UV Vis spectrometer. And then we said that if a molecule is colored or a solution is colored, that that colored solution could probably be ran on a UV Vis spectrometer. And I would dial in to a different range, and I could probably measure and get quantitative data based on that as well. Okay, so there's a lot of stuff that goes on here, right? You know, colors and the different colors and the complement colors and the proper regions of where I should be measuring these colors. And, you know, now we get this UV portion, and the UV portion has nothing to do with color at all that I can see. But I'm told that these molecules are probably absorbing in the UV region. I mean, there's a lot of stuff that's happening. And there's a lot of stuff to keep track of. And the easy part is that, you know, as a lab analyst, if you're working in a laboratory, you probably don't need to memorize all of that mess. Honestly, the only thing that I memorize is that if it's a non-colored solution, I probably need to be scanning 2 to 4. And if it's a colored solution, I probably need to be analyzing from 4 to 8 or 4 to 9. That's all that I have to remember working in a laboratory. The machine will do the rest, and the instrument will do the rest. So how do we get it to do that? What goes on? Okay, so let me give you an explanation of what happens. So, I take my sample holder, and my sample holder has my solution in it that I want to run. I have a light bulb. That light bulb shines light into the solution. Some of it comes out the other end, and the detector can pick up what my sample is doing. Well, this is the magic of the machine. Let's say that this sample is colored, and let's say it's blue. Well, I could, if I wanted, go to the color wheel, find blue, find the complement color of blue, find out the range that I should be scanning this sample, dial it into the machine, set it, and run it. But that's a lot of trouble. I don't want to go through all of that mess. I want something that's simple, clean, and easy, right? Just tell me some directions on what I can do with this colored solution that I can take it into a laboratory and do what I need to do without worrying about all of this mess. So, instrumentation manufacturers know that. And what they did is that they put an option on the machine called scan. And scan is just that. You're looking for something. You're scanning for something. What am I scanning for? Well, I've got a blue solution. I don't really know the number that I should be running. I can't remember it. So would you scan this solution and tell me the number that I should be running at, please? And the instrument goes, okay, yes, just put your sample inside, close my door, hit run, and I'll tell you what number you need to be looking at. It saves me a lot of headache. It saves me a lot of trouble. And that's the purpose of the scanning feature on the machine. Those old Cecils that we have a scanning feature on it. The newer instruments from Thermo, we have a scanning feature on that one as well. And the purpose of the scan, again, is to tell you what lambda that you should be running at. We know you're not going to remember the color chart. We know you're not going to remember the numbers of each color as far as the nanometers go. No one in their right mind would do it. So the instrument is going to help you out. And that is the purpose of this feature on the instrument. So I take my blue sample and I put it in the machine and I close the door. And I go into the scanning feature. And what happens is that the machine is going to question, okay, well, what would you like for me to scan? Well, you could give it the whole assortment if you wanted to. You could say, well, I'm not really sure. So I want you to start at 200 and I want you to go all the way to 900 and I want you to scan that window of wavelengths. And the machine will do it. It's a lot of work, but it'll do it. And it will do it in a couple of minutes. Doesn't take long. If you have a non-colored solution, well, you probably know you probably don't need to be scanning in the visible region. So if you have something that's non-colored, well, you'll probably want to scan between 2 to 400 nanometers. So that saves the machine a little bit of work. It saves you a little bit of time. It doesn't have to scan the remaining portion of 400 to 900. So that way you can analyze your samples a little quicker. If you know that it's a colored solution, then just go ahead and tell it to scan the entire colored region. Go to 400 to 900 if you want. So these are for colored solutions. Sometimes the instruments, though, they don't like the 900. They know that 900 is a little bit on the extremity. They know that it's the gray area. So some of the instrumentation manufacturers will actually change this 900 and it'll give you an error if you type it in. And if it gives you an error, you need to type in 800. The instrumentation manufacturers, it's typically one or the other. 800 is the max or 900 is the max. You don't really know which one you've got until you actually just type it in. If it doesn't like the 900, an error box will come up and it says, nope, sorry, too high. So just go down to 800. And typically, for the most part, it will accept 800 every time. So this saves me a lot of work. It saves me a lot of memorization. And what happens is that it begins to scan that window. All right, so down here at the bottom, I'm going to draw a graph. And let's say that I have a non-colored solution. But I'm going to scan the entire region, 200 to 800. I put this sample into the machine, I close the door, I hit scan. It says, what do you want me to scan? I type in 200, I type in 800, and I tell it to scan the entire thing. All of it, the UV and the visible portion, because I don't know squat about the sample. And I want you to tell me where the best number is that I should be measuring this sample. And the machine says, okay, fine, I'll do it, not a problem. Give me a couple of minutes, I'll go through the entire window, and I'll get back to you when I'm done. Okay, so let's say in the beginning, nothing really happens. So I just start to see a flat line that shows up on the computer screen. So 200, 201, 202, 203, 204, 205, 206, it's going 1 nanometer at a time. And it's measuring things to see if it can get anything at all from the sample that you've introduced into it. Nothing so far. Well, what happens is that eventually, sooner or later, my sample will begin to react with the light and I see a big spike. So the machine knows that and it says, oh, wait a minute. I'm in the window here. I know what numbers that I'm getting something from the sample that you knew nothing about. So I'm showing you that on the computer screen. I'm telling you that as I go through this window, I'm getting to a point of the buffet line that the molecule really likes what I'm offering. and we see a huge spike that goes up on the graph. Well, eventually that molecule has to continue to go through the buffet line, and it might see some of those items that it doesn't like on the buffet, and it passes those up. So what begins to happen is that this molecule begins to say, no thanks, I don't really like any of that stuff. And then it goes back down and it goes back to baseline. Okay, that is what we see on the computer screen. That is a scan. We're picking up the part of the buffet line that the molecule really enjoys. That's the purpose of the scan. Okay, well, we have a term for this. This is called the spectrum. All molecules have a spectrum. They can be simple. In this case, the molecule liked one item on the buffet line, and that was it. Didn't want any others. There are molecules, though, that are a little greedy, and they like to hoard up food on their plate. Numerous different items that they really, really enjoy, but they always have a favorite. So some of these spectrums can be a little more complicated than others. But this is what we would call a spectrum. And the purpose of the spectrum is to give me the favorite. Where in this range did the molecule really respond to the light energy that I'm giving it? Okay, well, at the top of this peak, that is a very important point. The top of this peak is the maximum. And if I draw a dotted line straight down, right here, that is the food item that it enjoyed. That is the wavelength that it really, really liked. So 2 to 8, let's say that this is about 325. So what the machine will do is that it will list 325 on the computer screen, and it will put the nanometer beside of it, and it will probably put the word maxima over to the side of that as well. And what the machine is telling you is that if you want to measure the sample, you need to dial in to 325, because that is the number that's the most sensitive for the molecule that you're running. That is the area of the buffet line that it really enjoys. And if you want to make this molecule happy and if you want to measure it, then this is the magic number that's going to allow that to happen for you. Again, we call this lambda because it's a wavelength, and we write the word max for maximum. So in a lab procedure or in a lab practical, if you see the word lambda max, that's letting you know that this is the area that's very special for that molecule. And if you want to measure the molecule, that is the number that's the best suited for those measurements. But sometimes you don't know it. Sometimes you have to scan it on your own and allow the machine to tell you where that lambda max is located. You can't find that in a textbook sometimes, or sometimes you can't find that in a lab experiment. You have to do it on your own. So if you are forced to do it, hint, hint, you need to scan the sample, find the lambda max, and then use the lambda max number for your measurements from that point on. But that is the purpose of the scan. So in the next video, we'll talk about a more complicated spectrum and how to handle those more complicated spectra.